Okay, so today we're really diving deep into the world of communication networks.
Yeah, the invisible highways of the digital age, right?
Yeah, exactly. And for our listeners, especially those third-year computer science students, this is um, crucial stuff.
Absolutely. This isn't just about understanding how to send an email or browse the internet. This is about the very systems you'll be working with.
Building on, maybe even revolutionizing one day. Now we're taking a deep dive into a chapter from Zelalem Lajee's Hallamariam's networking textbook.
A fantastic resource, by the way, really gets into the weeds of how networks function.
Totally. And today we're going beyond the basics, LANs, WANs, we're assuming you're already familiar with those. We want to really dissect those concepts.
Right, because the lines are getting blurrier, right? I
Yeah.
mean, we've got high-speed LANs that are pushing the boundaries of what a local network can be.
Exactly. So when does a LAN become a WAN? And then you've got these things called MANs.
Ah, yes, metropolitan area networks. Think of those as the middle child between LANs and WANs.
So like the network infrastructure for a whole city, right?
Exactly. Businesses, universities, even city services, all interconnected. Lots of fiber optic cables, super high speeds.
And then you've got WANs, which are on a whole other level. I mean, spanning continents.
Yeah.
It's mind-boggling when you think about it.
Absolutely. And the thing about WANs is no one really owns the whole thing. It's this network of networks all interconnected.
That makes sense. But how does data actually travel across these massive networks?
Ah, that's where things get really interesting. That's where we get into switching, specifically circuit switching and packet switching.
Right, and I know our listeners have probably heard those terms before, but trust me, there's a lot more to it than meets the eye.
Oh, absolutely. And understanding the nuances of switching is, well, essential if you really want to be a network wizard.
Okay, so let's start with the classic example of circuit switching, like a traditional phone call. It's like having a dedicated line, right?
Exactly. You place the call, the circuit is established, and you've got that dedicated connection until you hang up.
Reliable, but not very adaptable.
Right. Now, packet switching, that's where things get really interesting, and it's the backbone of how the internet works.
Okay, so walk us through it.
So instead of a dedicated path, data is divided into these little packets, each with its own addressing information.
Like sending a letter, but instead of one envelope, it's like 100 postcards, each finding its own way to the destination.
100 postcards, each with its own little map and instructions. That's a great way to put it. And because these packets can travel independently, it allows for dynamic routing, meaning they can take different paths through the network.
So that's how we can have so many devices connected to the same network without it getting completely jammed up.
Exactly. Efficient use of bandwidth is the name of the game here. But of course, this all sounds great in theory, but in practice, it gets complicated.
Oh, I bet. How do all those packets find their way?
So let's unpack the structure of a public telecommunication network, the kind that powers our phone calls, for example. Think of it like a hierarchy, really. You've got the subscribers, and that's us, the users, connecting through subscriber lines. They often call the local loop.
Okay, so that's how we connect to the wider network.
Exactly. And those lines, they converge at these things called exchanges, which are like regional hubs.
Makes sense. Sort of like central post offices, I guess.
Yeah, kind of like that. And then connecting those exchanges, we have trunks. Those are the high-capacity lines, the real heavy lifters of the network.
Okay, so it's all about connecting those exchanges efficiently.
Right.
But let's go back to those packets for a second. We left them kind of hanging there, hopping around the network.
Right, so imagine this. You're sending a large file, okay?
Hmm.
Packet switching. It doesn't just chop it up randomly.
There's a method to the madness.
Exactly. It divides that file into these manageable chunks called packets, and each one gets a header.
The header, that's where the magic happens, right?
Exactly. That header, it's like the address label on a package, but way more sophisticated. It carries the source and destination addresses, sequence numbers, error detection codes. It's like a whole instruction manual packed in there.
So it's not just about getting there, it's about getting there in the right order and making sure everything arrived intact.
You got it. And each packet, it travels through these things called nodes. Think of those as network intersections.
Okay, so at each intersection, the packet has to figure out which way to go.
Precisely, and that's where the header information comes in. The node uses that information to decide the best route. And that route can change, depending on traffic, congestion, all sorts of factors.
Sounds incredibly efficient, but also like a lot of things could go wrong. What if a packet gets lost along the way? Or delayed?
That's actually one of the strengths of packet switching. Unlike circuit switching, where a dropped call means you have to start all over, If a packet gets lost, it can be retransmitted without disrupting the entire flow.
Oh, that's clever. So it's more resilient than I thought.
Exactly. But you bring up a good point about delays. That's a big one, especially with applications that are time sensitive, like video streaming.
Right, because you don't want to be watching a movie and have it constantly buffering.
Exactly. And those delays, even small ones, can be a real problem. We call that variation in packet arrival times jitter.
Jitter. Sounds almost cute for something that can cause so much frustration.
Right. But high jitter, it can make real-time applications basically unusable. Minimizing jitter, that's a huge challenge in network design.
I can imagine. So we've got these packets, they're finding their way through the network, sometimes encountering delays, sometimes getting lost. What happens next?
So within packet switching itself, there are actually two main approaches, datagram and virtual circuit. Both of them use packets, but their philosophies, how they handle those packets, it differs.
Okay, let's break those down. What's datagram all about?
Datagram, think of it like the independent traveler of the network world. Each packet is treated individually. It figures out its own best route based on real-time conditions.
So they're not necessarily traveling together.
Nope, they could be taking completely different paths. And that means they might arrive at the destination out of order.
Out of order. So how does, the receiving end know how to put them back together?
That's the thing. The receiving end, it has to reassemble them in the correct sequence based on the information in those headers we talked about. It's like sending a puzzle, but each piece is mailed separately.
Okay, that makes sense. It's efficient, but it relies on the receiver to put it all back together.
Yeah.
Are there any other advantages to using datagram?
Oh yeah, it's super flexible. You don't need to set up a dedicated connection beforehand, so it's great for applications where connections might be intermittent, like email, for example.
Right, because with email, you're not constantly sending and receiving data.
Exactly, so that's datagram. Now, virtual circuit, it's a different beast altogether.
Okay, so how is virtual circuit different?
Virtual circuits are more like, say, taking a pre-booked train journey. Before any data is even sent, a route is established through the network, and all the packets for that transmission, they follow that same path.
Ah, so it's like reserving a lane on the highway, but for data. Everything stays together, nice and organized.
Exactly. And because of that, virtual circuits, they tend to be faster, more predictable. They're great for applications where that kind of consistency is super important, like video conferencing. You don't want things arriving out of order there.
Right, that would be disaster. But if it's a pre-planned route, doesn't that make it less adaptable than datagram?
That's the trade-off. If something happens along that pre-planned route, if a link goes down, the whole connection's affected. Datagram, it can just reroute those individual packets.
So it's about choosing the right tool for the job, really. Datagram for flexibility, virtual circuits for consistency.
Precisely. But no matter how efficiently we route those packets, there's another layer to this whole network puzzle that's absolutely crucial, especially as we demand more and more from our networks.
And what's that?
Quality of service, or QoS. It's not just about getting the data there, it's about making sure it gets there with the right level of performance.
Okay, QoS, quality of service. It's like the VIP treatment for certain types of data, right? Making sure they don't get stuck in traffic with everyone else.
Exactly. It's about recognizing that not all data is created equal. Some applications, like, say, streaming a live video, they need super fast, uninterrupted delivery.
Right, because nobody wants to watch a live stream that keeps buffering every few seconds.
Exactly. Whereas downloading a file, yeah, it needs to be accurate and complete, but it doesn't necessarily need to be instantaneous.
So with QoS, you're basically telling the network, hey, this data is important, prioritize it.
Precisely. And the way we do that, well, there are a few different approaches. One way is what we call over-provisioning.
Over-provisioning sounds like overkill, maybe?
In a way, yeah. It's basically just throwing a ton of bandwidth at the problem, make sure the network is so uncongested that even if you have a lot of high-priority traffic, it's never an issue.
So like having a 10-lane highway for just a handful of cars.
Pretty much. It works, but it can be incredibly wasteful, especially since network traffic. It ebbs and flows throughout the day.
Right, so you're paying for all that capacity even when it's not being used. So what's a more elegant solution?
Prioritization. That's where we start getting into the real nitty-gritty of QoS. And there are two main flavors of prioritization, with guarantees and without.
Okay, so what's the difference?
Think of prioritization without guarantees, like having a fast lane on the highway. You might still hit some traffic, but generally speaking, you're going to get where you're going quicker.
So it's like a best effort kind of thing.
Exactly. We mark certain types of traffic as higher priorities, so they have a better chance of getting through quickly. but no promises. Now, prioritization with guarantees, that's a different story.
Okay, so this is where we get the real VIP treatment.
This is like having a private lane on the highway, nobody else allowed. We use strict rules and we actually reserve resources to guarantee a certain level of performance no matter how much other traffic is on the network.
So if you absolutely positively need your data to get there on time, that's the way to do it.
You got it. It's essential for applications where even small delays are unacceptable. But, of course, it comes with a cost. It's more complex to manage, and you might not be using your network resources as efficiently.
Right, it's a trade-off.
Yep.
So with QoS, there's no one-size-fits-all solution.
Exactly. It all depends on the specific needs of the network and the applications running on it. And frankly, that's what makes networking so fascinating, so challenging.
It really does. I mean, who knew there was so much going on behind the scenes every time we load a web page or stream a video?
Right. It's easy to take these things for granted. But as computer science students, as the future architects of this digital world, understanding these concepts, it's not just about passing an exam. It's about building better, faster, more reliable systems for everyone.
Absolutely. It's been an incredible deep dive into the world of networking. Really appreciate you walking us through all of that.
My pleasure. Always happy to talk networks.
And for our listeners, keep exploring, keep questioning, and most importantly, keep learning. The world of technology needs more curious minds like yours. Until next time, thanks for joining us on The Deep Dive.